Swayamprabha. Digital India. Educated India.
Hello. At the end of the last class, we made a list of a few applications of sprays, and what we are going to do today is sort of zoom out a little bit and look at spray as an entity. Spray is a collection of about a million, billion, maybe even a trillion drops, okay, and we want to see what sort of measures can I bring to a spray to gain a quantitative understanding of a spray. So, we will start to make a list of a few different spray characteristics. Now, before we turn to the audience and try to ask this question of them, I want to suggest that there are basically two kinds of spray characteristics. One that are macroscopic in nature, and a second that is microscopic. Okay, so, we will make a list of a few different macroscopic qualities first. And then move on to the microscopic qualities. We will just take a steady spray. So, as opposed to a little perfume spray is where you push the plunger down, a whiff of perfume comes out, there is a start and an end to it. Okay, so, we are going to talk about a spray that has no start and an end, okay, but it is just like a continuous perfume spray. It is just easier to understand these qualitative aspects in that context, and then we will talk about an intermittent spray also, and talk of some qualities of an intermittent spray as well. Okay, so, let us start listing a few different macroscopic qualities.
Macroscopically, the spread, how much area it spans.
Okay. So, we will just say spread or span of the spray. Spray angle, very nice. Okay, I will also distinguish this between this and cone angle. Okay, we will talk about that also. Penetration length. Droplet size, okay, we are going to list this in the, I will distinguish this because this is going to occur in both the macroscopic and the microscopic list. Okay, so, we will talk of this in just a moment. Macroscopic measure. Okay, any others that we want to include?
So, this droplet velocity.
Velocity. So, we will just say velocity as again a macroscopic measure. Okay. So, we have already made a list of a few different things here. So, and I want to add one to it, which is one that is relevant to many different processes, actual mass flow rate of the liquid. We can add a few more, but this is a good enough list. Okay, so, if I just take a typical spray, let us say I have a spray nozzle from which I have the spray emanating. Now, first of all, I have this all these drops in the spray, we have seen this many times. The actual flow rate coming out in a steady sense is the liquid mass of the liquid flowing out per second. Okay, this is relevant to surely many applications. Okay. Now, talk of velocity, there are two kinds of velocities. Okay. The reason I wrote down macroscopic measure is because I want to know sort of in a bulk. So, if I take a whole bulk of this spray, what is like a velocity vector of that bulk? Okay. But really speaking, it is not of use to know what this whole bulk is doing. I want to know what different points in the spray are doing. Okay. So, therefore, there is a need to understand sprays using microscopic measures. Back to the macroscopic, I just want to complete the list here. Spread or span, like for example, that width at a target surface. Say for example, if you are spray painting a wall, I have the paint can about let us say 10 inches away from the wall. When I push the plunger, and this is a continuous spray because I can just walk along the wall and paint the wall. When I am walking along the wall, there is a certain width that the paint impact will cover. That is important because I want to know how many passes I have to make of this can. So, if I look at a measure like that, that gives me a width, and clearly that is also tied to the cone angle or the spray angle. So, there are two kinds of angles and we will talk about them maybe about a week from now, but essentially if I call that angle 2 theta, 2 theta is what we will call the spray angle. The cone angle is slightly different, we will look at that in some detail, in the sense that the angle very close to the nozzle here would be slightly different for different fluid mechanic reasons, and that is often referred to as the cone angle. So, you have a cone angle that is usually larger than your spray angle. Penetration length. Now, again some of these measures are all tied to each other, because if I take a spray of a certain mass flow rate and somehow increase the width, which also means increase the spray angle, I am naturally going to decrease the penetration length, because the drops on sort of the mass of drops are going to slow down. So, the penetration length is a measure of that. Alright, so let us put this intuition to work. We will look at a little video we made in our lab here. This is a simple perfume spray that is going to go from start to end. Okay, so let us play this video and see what we learn from it. I want to pause it there to point to a few different things. You look at that angle there, that is the spray angle. Now, as you go further downstream, you can see that the spray angle becomes less and less defined. So, as I go further and further downstream, the spray angle becomes less and less defined, because there is no spray edge. The idea of a spray edge is an illusion. It is not like the edge of this pen, the edge of a pen is well defined. The edge of a spray has to be defined by us, and our definition of the spray edge is going to also influence our definition of the spray angle. So, if I say I want to go as far as I find no drop at all, that is going to give me an almost 180 degree cone angle in many different sprays. It is going to be a very large number in comparison to where I said I am going to go to a point where the mass flow rate drops below some critical value. So, mass flux, okay, that is the rate of mass flow per unit area drops below a certain value. So, I will say okay, when there is very few drops, almost a mist, I am not going to count that in my spray. That is a simple definition of a spray edge. We can find more quantitative definitions as well, but our idea of a spray angle is clearly tied to that. Okay. Alright. So, here let us go on and continue to play this video. I want you to understand 2 or 3 different aspects here. you can see that there are some big white flashes right where my mouse is pointing. Okay, those are in a sense big drops. So, I can go back to the start and show you where they started. You see that drop there that started is going to continue forward. I want you to notice two differences here. One, of course, this is not a steady spray, but this idea also applies to a steady spray. So, the concept of having big drops alongside tiny drops is not something that is out of the ordinary. Every spray of any commercial interest will have a range of drops that the spray has. So, typically the range is on the order of at least two orders of magnitude in span, more often it is 3 orders of magnitude in span. So, the idea that you have drops that are ranging from nearly let us say a fraction of a micron or micrometer in diameter to hundreds of micrometers in diameter is not at all out of the ordinary. In fact, you can see this in this image. Okay. Now, as you keep going, you can see that the perfume has practically stagnated around, and there is not much movement of the drops past that point. So, you spray and the spray goes into air and sort of the drops reach due to the drag from the surrounding air, they sort of equilibrate. They may continue to move forward by momentum conservation, but it is diffused quite a bit. So, your spray width starts to increase as you go far downstream. Okay. So, now when I go back and look at that, like I said, there are many different microscopic properties that are actually more important and relevant to a spray. Like for example, at every point we said you are going to have a drop size distribution. So, I said point, but we will qualify that in just a moment. The idea that a spray is composed of several sizes of drops. Okay, this is sort of obvious to us by now. Not just that there is also a velocity distribution. Okay, again I will qualify this. To clearly distinguish it from the air around. Okay. We are looking at a droplet velocity distribution. So, you have drop size distribution and droplet velocity distribution that are all microscopic properties. So, these are now like I am looking at the individual droplet level, I am almost looking at somehow understanding the spray from within as opposed to from without, from outside. Okay, what other microscopic properties can I list here? I can look at in a typical spray like a perfume spray, we looked at this yesterday as well in the last class. We are interested in like a rate of evaporation or temperature dependence, which is clearly temperature dependent. Okay. So, from there I can say somehow there is also this idea that there is a droplet temperature distribution. Okay. So, these are all in some sense individual variables, like a drop, a single drop has a size, it has a velocity and it has a temperature. These are all at the droplet level, they are properties that you can assign to a single drop. Now, at the spray level how do I convert this droplet level information into a spray level information? Okay. There are two ways of doing it. One, I do just this. So, I sit here, play this video, or I have a spray like this going, I pause. Okay, I pause the picture and then look at all the drops in this frame. Now, this particular video is not particularly good to zoom in and zoom out, although you could to some extent, it is not quantitative, but clearly that is just a question of camera resolution. So, if I have a sufficiently high resolution camera, and these are not out of the ordinary also, I can pretty much image every drop in this frame right now. Okay. And from the image of every drop, I can reconstruct the size of every drop. So, let us say we did this calculation last time, there are approximately a million drops in this picture right now, probably slightly less than a million. I can image every drop, get a size and get million numbers. Okay. From that I can construct a histogram of what to do with this. So, once I go to the million drops in the picture, so sample, so let us first pose a question and then we will answer, what is drop size distribution. So, I want to understand what do I really quantitatively mean by drop size distribution and how do I measure it, that is what I want to get to. We will spend quite a bit of time on this how do I measure it thing, but I want to first start with what is drop size distribution and then that will naturally lead us into how do I measure it. If so I can take a freeze frame, count every drop, in the frame, and measure its size. Okay. This will give us essentially like a million numbers or slightly less than a million numbers, and from there I can construct a histogram. We are all familiar with the concept of a histogram. Okay. I want to spend some time on that because there is some very important mathematical tools that we need to acquire to completely understand what a real histogram and what we can do with a histogram. Okay. So, let us say I do this histogram and it gives me something like this. So, this is diameter and this is count. I can get the count versus diameter of every drop in this frame and that will give me a distribution. Okay. Clearly, this is a drop size distribution in the spray. This kind of an information is what we will call spatial drop size distribution, because my independent coordinate of acquiring this information was x and y, the space. Another way of thinking at it is, thinking about this is, for every drop that I capture or count in the freeze frame, I can also get its x and y coordinates. Okay. So, that automatically means I am in the process of acquiring the spatial drop size distribution, because those x and y coordinates would be different for different drops. Okay. Another way of getting the same drop size distribution is to sit at a point in the spray. So, look at where my cursor is. I will sit at that point in the spray and I have a way of just sitting in a lawn chair and counting every drop that is going by me. Okay, so I am not moving in spatial coordinate, I am just sitting at that one point and acquiring information of the droplet size, droplet velocity, droplet temperature if I want to really get specific about the spray, of every single drop going by me. Okay. So let's look at that. Another way of doing the same thing, so I can look at every drop in the spray that is going by me and get its drop size, velocity, in this case it could be a vector, it could be both a x and y coordinate, and temperature if I really want to get fancy, of every drop. Now the independent coordinate that distinguishes different drops here is the time of arrival. There are succession of drops coming through, so every drop is going to have a different time stamp of when it arrived at my location, okay, as opposed to the previous way of sampling drop size distributions where I had the distinguishing feature, it was a x and y coordinate of the drop. Okay. So I can now take this same, let us say I sit there for 10 seconds, and in 10 seconds, like typical perfume whiff is like let us say 2 seconds, and in 2 seconds I was able to sample, let us say again a fraction of a million drops, and I have now statistics of size, velocity of every drop coming through there. So I will just for now ignore the other quantities and look at only the size to sort of illustrate the point. So I can now do the same histogram . Okay. I will get again the independent coordinate of this histogram is the same, I am counting the number of drops in a certain bin. Okay. Now this distribution is what we will call the temporal drop size distribution. Okay. So we started to talk of microscopic measures, of which drop size distribution is one measure, and when we listed this here, it was actually a fairly simple thing to list. There is different size drops, we want to understand some information about the size drops. We quickly found out that there is not one, but there is two different drop size distributions. Now we are left in a limbo. Okay, are they the same, or under what conditions can we expect them to be the same, under what conditions will they be totally different, because they contain different pieces of information. Okay. So before we completely understand under what conditions are they the same and under what conditions are they different. Okay, I want to sort of make the equivalence between these two ways of sampling the same problem, sampling the same physical system. You are essentially measuring something about a physical system. There are two ways of understanding any physical system. Okay. One is what is called a random field approach, especially a statistical system like a spray, that is like some sort of an uncertainty, some sort of a you have to resort to probabilistic measures at some point, and under those situations there are two ways of doing it, either a random field approach or what is called a point process approach. Okay, we will talk about this in some detail, but I want to sort of draw the equivalence between a field approach, that is where I am looking at a spatial distribution of some quantity and a temporal distribution of another quantity as being two completely different ways of looking at the same system. So, in general we do not expect them to be the same, they are completely different. Okay. Under what I will present one simple situation under which they will exactly be the same. So, if I say for example, when are the the same is a very restrictive criteria. Okay, I want to start with that because that is the easiest to understand. They are exactly the same. When you do two things, one, if I take a spray, and in this case I cannot do a spray like a usual spray, I take drops in a box. So, this is a box that has all these drops in it. Let me not clutter the box with it. Okay, there are different size drops. If every drop in this box was moving to my right with exactly the same velocity. Okay, so, all the drops are moving to my right with exactly the same velocity. Then if I had a way of staying at this location, I will call this x, sample drops So, I am not sampling drops at a point, but I am sampling drops passing through a certain cross sectional area, and this is also possible, measurable and quite routinely done. So, if I am able to sample drops passing through a certain cross section and I construct a drop size distribution from the sampling at a certain cross section, this is like my temporal drop size distribution. And if all the drops were moving with exactly the same velocity, okay, then essentially in the time, let us say if the width of this box was some delta, delta divided by u is the time taken for all the drops to pass through my cross section. So, whether I take a snapshot at some time t equal to 0 of this box or and then construct a spatial drop size distribution from all the drops in that box, or whether I sit at location xx and sample all the drops come through that cross section and then construct the same distribution, I will get exactly the same answers. Okay. So, really speaking, there are two assumptions I made, not one. One assumption is that all the drops are moving with the same velocity. Okay. I showed you where I am going to show you where I cheated you into another assumption. Okay. So, one assumption the second assumption is this. Let us say this box is my frame, correct. This is the frame that I used to construct my image frame that I used to construct my spatial drop size distribution, and then I am sampling for a certain time t, capital T, that is going to tell me the time over which I can sample to get the temporal drop size distribution. Okay. So, if delta is the width of this frame and capital T is the time of sampling, it is only when capital T is exactly equal to delta divided by u that I get this. If I choose capital T to be some other number other than delta divided by u, let us take the simplest situation where capital T is less than delta divided by u. Okay, what happens if capital T is less than delta divided by u? I would have only sampled a part of this frame. I would not have sampled the other half of the frame or other part of the frame, which means now is there a guarantee that the drop size distribution I construct from half the frame is the same as the drop size distribution in the full frame? There is no guarantee. I could have had a completely different mix of drops in the back half of the frame, I do not know that, right. So, this criteria that capital T has to exactly be equal to delta divided by u. So, in other words, if you made a freeze frame of a spray and you reconstructed a drop size distribution, even if all the drops were moving with the same velocity, I am constrained to sample at this capital T only to get the exact same distribution, which is again very restrictive. So, T has to be exactly equal to delta divided by u. This is not so obvious. Okay. Now, clearly the first assumption and the second assumption are different in the basic philosophy. One, assumption number 1, I have no control over what actually happens in the spray. All drops have to move at the same velocity, I do not get to control that. But the second looks more like a measurement thing. Okay. The second looks more like, so even if all drops are moving with approximately the same velocity, can I make this equivalence? The only way to make that equivalence is if somehow, even if you make spatial drop size distribution measurements with some delta, I make with another t. Okay, I do not know what delta you used, but I make it with some other t. What sort of delta and t will give me approximately the same information? Okay, or at least on what sort of delta and t relationship will give me information, will allow the two kinds of distributions to tend towards each other. The answer to that is, as I keep making my delta larger and larger, so your initial spatial size distribution is composed of a very large frame and you had enough resolution to actually size every drop in the spray. And then I can take a time sampling that is also very large. So, I can sit there for ever and ever and ever and then sample all the drops. So, if delta became infinitely large and t was also infinitely large, all I need to know is then they are going to be approximately the same, given that the drops are all moving with the same velocity. Okay. So, essentially the second criteria is an artifact of the idea that we are constrained with finite domain sampling and finite time sampling. Okay, the fact that I cannot sit there and measure forever and ever, I have to do my sampling in a finite time. Likewise, my camera cannot zoom out to the entire region of the spray, I am only constrained to a small part of the spray. So, these are the sort of the assumptions that underlie the equivalence between the spatial and the temporal drop size distributions. Now, what about velocity? Let us talk a little bit about velocity as well, and then we will move on to the third part. So, we will look at what velocity distribution is. Again, if I go back to my image, I can pause the image, I can okay, this is a paused image. I can take another freeze frame just like this a short time thereafter and use some fairly simple algorithm, simple or sophisticated, to find the displacement of a drop. Okay. So, it is like we are going to get into this in some detail towards the end when we talk of measurement techniques, but essentially I can image a drop, image a set of drops now and a short time later, and from those two images I can reconstruct a velocity field. Okay. So, one way is take images a small time apart Another way of doing the same thing, see how this is equivalent to the spatial information. What distinguishes every particle here is its original x and y coordinate in the image. So, if the original x and y coordinates are of every particle in this in the original frame are different, like we started to do with, like we discussed with the drop size distribution. The second way of doing it is exactly like the previous temporal size distribution, which is I sit at one point and measure the velocity of every point coming through, every drop coming by me. Okay, so, I can sample the second way. So, these are two different ways, again like we discussed with drop size distribution, it is not obvious that they have to be the same. In fact, in the case of velocity there is no reason to even believe that they will be the same, because drops at different points are different. So, in other words, I cannot even start to ask the question under what conditions will these two be the same, because they are two completely different pieces of information. Temperature and other, like we discussed towards the end of the class last time, we talked of concentration as being a parameter that qualifies each drop. So, if I have a fuel that I am spraying that has multiple components, concentration of a certain component in a given single drop is a scalar measure that is associated with that drop. It is like a scalar property, not a measure, scalar property associated with that drop. So, I can have this temperature is also another scalar property associated with the drop, vector is a velocity is a vector property associated with the drop, size is a scalar property. So, I can get into lists of vector and scalar properties associated with these drops. But the point is all of those properties can be measured in a spatial sense or in a temporal sense. Okay. Now, the basic requirement for equivalence between these two is that we will only focus on the first one, that all drops have to be moving with approximately the same velocity, if not exactly the same velocity. That principle is very often violated in a real spray, and therefore, these two measures are completely different, and that violation is quantified in terms of what is called as size velocity correlation. Correlation, the word has a meaning that there is somehow there is a, if not a causality, meaning somehow there is a sense that a certain size drops can be expected to move with a certain velocity, that is known a priori. Okay, that is the idea of a correlation. So, I can now take this spray for example, and when I play it, you can see in here that the larger drops, for example, right in the middle here, are moving with a slightly higher velocity compared to the smaller drop at exactly the same spatial location or very nearly the same spatial location. So, at least as far as this spray is concerned, larger drops are moving with a higher velocity in comparison to the smaller drops, and that is basically information that I can take to, if I measure that in this perfume spray, I can transport that information to another perfume spray that is somewhat similar in construction, and I can apply this information to other processes as well, where even if the nozzle design was not the same, fluid mechanically if they were similar, then larger drops in that other spray can also be expected to move with a higher velocity in comparison to the smaller drops. And in general, in many different sprays spanning many different nozzle designs, at any given point the large drops will tend to be moving slightly faster than the smaller drops on average. Okay. So, this is the idea that this is a very important word, because I cannot draw any conclusion on any two given pairs of drops. If I give you two drops at a particular point and asked you the question, is the larger drop moving faster? Can you for sure predict if the larger drop is going to move faster? You cannot make that prediction. All you can say is, on average, in a fairly large sample of similar drops, similar large drops, similar small drops, the similar set of large drops is expected to move slightly faster than the similar set of small drops. That is the only prediction you can make, and that is the only idea that you can take away from a size velocity correlation. Now, all of the measures that we talked about, all of the spray characteristics, both macroscopic and microscopic that we listed thus far, are only sort of steady spray characteristics. So, these are, we have discussed them thus far in the context of a spray that has no beginning and end in time and that is relatively unchanged in time. Okay. So, let us sort of make sure we completely understand what we mean by steady, because it is a very important we say we are making the steady flow assumption all the time. Let us understand what we mean exactly by that word steady spray in the next few minutes. Let us take the spatial distribution as our means of understanding steadiness. So, I take a picture and I have reconstructed this drop size distribution. I take a second image and a short time later, let us say 1 second later, and these two images are exactly alike. Okay. Now, clearly they will not be exactly alike, all I have to say is they are alike. So, without going into the microscopic detail of which drop is at which x and y location in the image, if I can take two frames, okay, that I took some time later and I am unable to tell which one was taken first. So, the time stamp is indistinguishable, the time stamp is not encoded into the picture itself. That is the case of a steady spray. Okay. So, if I go back to my old high speed video, if I took this picture and then this picture, the first image had the spray only about that far, the second image has a spray almost further downstream. That is the nature of how a perfume spray works. This is a clear case of violation of my steady definition. But if I drag this further down into my high speed video and now play it, I took this image, or I will go back. Okay. I took this image and then another image a short time later. Now, this is still a transient spray as far as my eye is concerned. I mean, there is a start and an end, but there was a time in the middle, say about 1 second, when I could not tell two images that came 100 milliseconds apart. Okay, so, these in that time span, there was a time span in the case of a perfume spray when I can treat the spray to be relatively steady. Okay. So, our basic definition of steady, okay, for the case of this class, okay, is that if I take two pictures of a spray and I cannot from all macroscopic measurements, okay, I am starting off with a less constrictive criteria first and then we will talk of the microscopic case. I cannot tell which one came first, okay, then I am beginning to make the case that they are steady. Then if I make microscopic measurements of the drop size distribution, so I am now recovering the statistics of the spray, be it temporal or spatial. If I can still claim that I cannot tell the difference as to which one came first or which one came next from the microscopic measurements of distributions, I am still okay, I can still call it a steady spray. When I can begin to tell the difference, like the first example we saw with the startup, I can from a macroscopic measurement of a penetration length tell you that they are not the same, I can tell which one came first. So, that is not that is a clearly unsteady spray. So, if you take a clear case like a diesel engine where you have your injector operating a few hundred times a second, can I use any information from all this literature concerning steady sprays for diesel sprays? The answer is yes. The answer is pick up the time window where you cannot tell the difference, and there is a time window. As long as you restrict the application of these models to describing the spray in that time window, you are doing quite okay. Okay. So, just as a quick recap, we talked of different measures or different characteristics of spray and then we talked of spatial versus temporal measurements and the equivalence thereof. Okay. And then finally, we made the case for a steady. What do we mean by steady spray? Okay. We will continue this discussion in the next class.